Hello everyone, my name is Harman Singh, and within this video, I'm going to go over coverage-based Greybox fuzzying as Markov chain. This is a research paper I decided to talk about. And so the historical context here is that this paper was originally published at the ACM Conference of Computer and Communication Security. And this paper mainly pertains to coverage-based Greybox fuzzers, right? And the first of its kind was AFL, and it was introduced by Michael Zalewski. And with the introduction of AFL, the first of its kind, and sort of introduced in late 2013, and was finding an incredible amount of bugs and vulnerabilities up until 2015 and 2016, right? It sort of showed that you didn't need intense analysis in order to achieve vulnerability detection, right? And one downside, though, to this approach was the way that this was founded, right? This whole approach of coverage-based gray box fuzzying was not through some sort of rigorous mathematical approach or any sort of formal model being derived. It was sort of just loosely figured out, right? And so that sort of raised an issue. There was a lack of a formal model, and there was a lack of a framework, right? And so the researchers within this paper decided, okay, let's see if we can sort of come up with some sort of model to work off of and sort of describe how AFL behaves and then see if we can create optimizations off of that. And so 2 months prior to actually publishing their paper, they submitted AFLFast, which is, based on their paper modeling AFL off of a Markov chain and then applying optimizations that they found from the model and then submitted it into the DARPA CGC finals, which the DARPA CGC finals, or the CGC standing for Cyber Grand Competition, essentially DARPA wanted to invest a lot more money into automated bug finding and vulnerabilities. And they submitted AFLFast 2 months prior to publishing their paper. They actually placed second, competing against a variety of other vulnerability finding tools, right? And after that, 2 months later, the paper was published and helped provide some sort of theoretical foundation to work off of, right? Of course, there were some flaws, which will be discussed towards the end, but it was the first of its kind to actually bring some sort of model, some sort of framework, to sort of reason about this, not just like the fuzzer's not really working because it's not exploring some paths here, some paths there. No, it's now it's like, okay, we can actually break this down into a rigorous model and try to come up with something based on something a little bit more formal, not just loosely grasping at what we think might be happening, right? Now let's move on to the abstract. We can see that CGF stands for coverage-based gray box fuzzy. Right? And so the term gray box here sort of implies that there are other categories of fuzzying, right? And there are. There's white box and black box fuzzying. White box fuzzying uses program analysis to better generate test cases. However, it is more computationally expensive since more time is spent actually trying to create meaningful test cases, right? And so you might actually run into a situation where a white box fuzzer may not perform as good as a black box fuzzer. And black box fuzzer in this case is a fuzzer that generates purely random inputs with no feedback mechanism to tune the test cases. And so CGF comes in trying to provide a middle ground solution using lightweight instrumentation directly into the program binary to get code coverage as you execute inputs. And from there, that allows you to explore new mutations you generate and lets you sort of steer the randomness as you're um, using your fuzzer, right? And so you're able to reduce the computational expense uh, experienced by a white box fuzzer while not being purely random and all over the place as a black box fuzzer. And sort of the way this is done is to recognize that a lot of test cases may end up having overlapping paths or very similar code coverage, right? And so if a lot of inputs are covering the same things, do we want to spend more time on them? maybe we would want to spend more time on inputs that are exploring more isolated parts of the actual program. And so, how do we explore these less common paths? How do we use Markov chains to establish this? And why is the resulting AFLFast so much better, right? Because these tie directly into the paper and sort of what it goes deeper into. And before moving on, let's um, look at the introduction, right? And so with the introduction, there's some terms defined. And so there are three functions, S, F, and P. S refers to given I a test case, it'll give you how many times it has been picked. And F here, of course, has the same parameter here, I, but it refers to something a little bit different. It is the path associated with a test case after it has been run. And you get its path, right, from the instrumentation. And this path represents its code coverage. You plug its path into this function, and then you're able to see, okay, how many times have we run into this? And then you increment it because you have just now just ran into it again. And what this tells you is, okay, is it worth exploring this even further if, we've run into this a bunch of times, right? And P here represents the amount of times you want to fuzz a certain seed. Once you've sort of selected a seed, how many times do you want to keep on fuzzing it? How many times? Thousands, hundreds of thousands, or is it going to be some sort of function? And so I here is going to be the same as it is for S. It's your test case. Um, and then from there you establish, okay, this is how many times I want to fuzz this, right? And the function P here is mainly used for power scheduling, determining how much energy you want to give to a seed or a test case, how much computational expense you want to attribute to that one case in order to explore it further. And then search strategy is attributed more to S, where or a combination of S and F in order to really determine, okay, which seed should I pick next, right? And then AFL versus AFL fast, they, for the most part, have the same underlying algorithm, which we're going to describe loosely very soon. But AFL fast differs in how it distributes energy amongst test cases and how it decides to move on to the next seed, right? And how it does so is, of course, through using Markov chains as a model, right? And we're going to explain what that is and sort of how that ties into this, right? And so it's important to understand how AFL actually works. And so the program itself within this actual binary contains various branch points. And at each of these branch points, we're going to insert this coverage instrumentation, which is this code snippet right here. If you see, each branch point is assigned a compile time random value. And we take the current location value and previous location value and perform a XOR operation. And from this, we're actually given a indice within shared memory that we increment. And so essentially, if we've made it to this branch point, right, current location is assigned a value. And then from there, we're able to perform a XOR operation in order to get sort of perform some sort of hash in order to figure out, okay, where does this edge map to within shared memory, and then increment it by one since we have now ran into it. And before moving on, we actually shift current location over one and set previous location to this value. This is essentially to prevent, like for example, if we go from node A to B, that's edge AB, we want that to be distinct from BA, right? So in order to do that, we shift current location down by one. And so if the XOR operation is performed, right, that edge B to A will be mapped to a different value. But we are still able to get to that indice within shared memory and increment it, sort of being able to show and mark that we have crossed this edge, right? And so that gives us the ability to sort of distinguish the two using this very quick, lightweight code snippet sort of distribute over these branch points, right? And shared memory in this situation is 64 kilobytes. So, it's not, too substantially large in terms of memory. And so now it's important to understand how the actual AFL algorithm works because we know that AFL and AFLFast share the same fundamental algorithm. However, they differ in how they choose their seed and assign energy to each seed um, when exploring them, right? So if we look here, TX signifies sort of the crashed inputs that we have discovered so far. And we also start with a set T, which represents, okay, these are our initial seeds. However, if no seeds are actually given, then we'll just start with an empty file and begin from there. And AFL uses a seed strategy in order to determine the next seed simply by just looking at the next seed within the queue, and the queue here being circular, so we'll just start back from the beginning. So we just go and start with the first one, assign it some energy, which for AFL is a constant amount of energy, right? We're basically spending a fixed amount of energy per seed every time we move on to it. And from, 1 to P, right? The amount of energy we assign, we're going to generate that many test cases, right? Because that's sort of the energy corresponds to here, how much we're going to fuzz this seed we've chosen. Right? If it crashes, we add that to the, sort of the set representing this T sub X. Otherwise, if it ends up being an interesting case, then we're going to add it to T and explore it further, right? And of course, interesting here is lighting up part of the code that has not been previously lit up before, right? And this would then be added to T to be further mutated and explored, which, using T and P and sort of the choose next and assign energy and how they work, right? This is done in order, and eventually each seed is assigned the same energy, and right, it's each seed is essentially given the same attention, and there's no real critical way to choose or meaningful way really to pick the next seed, right? We're just sort of going to what's next in the circular queue, and it just keeps running until time runs out or um, some sort of abort signal is sent through. In order to better understand why the procedures made the changes they did to the seed selection strategy and the energy distribution strategy within the original AFL algorithm, we need to understand the model that they end up describing and what they're able to get from that model. But in order to even comprehend that, you need to understand what a Markov chain is. And so a Markov chain is sort of movement between random states such that going from one state to another doesn't depend on your previous history of states, rather the current state you're at. For example, if today is a rainy day, then the odds of it being cloudy is 0.5% the next day. If we look in the graph in the corner, and it's 20% chance of it being sunny the next day, or 30% chance of it being rainy again. It doesn't matter what the weather was within the last week. What currently matters is the weather that it is today. And these probabilities are neatly compacted into a transition matrix. And so this transition matrix, if you were to sum along the rows, you end up getting a probability of 1. Um, and let's say, n is the number of days we've been walking through this graph. Let's say we keep on doing that for tens, hundreds, thousands, and start going towards infinity. And we keep track of, the frequency of how many days it's rainy, how many days it's cloudy and sunny. We'll end up finding that those values end up converging, right? And pi sub I, right, the standard distribution represents frequency for a given state, right? And time homogeneous in this case means as time is moving on, the probabilities associated with a given state do not change. So on day 0 versus day 999, probability of, if it's a rainy day, its outgoing probability should still be the same. It shouldn't be different. If it was, then we run into a time inhomogeneous Markov chain. And that sort of opens and introduces a new set of problems. So now sort of dive into we need to understand about time homogeneous and time inhomogeneous Markov chains and a brief overview of how they're sort of discussed. And now let's talk about the time homogeneous model that the researchers discuss in the paper. Originally, the researchers realized that the real process is time inhomogeneous, right? Different inputs on the same path will end up resulting in different transition probabilities, right? And so by simplifying it, focusing only on paths and non-specific inputs, you end up getting fixed transition probabilities, which makes it a simpler homogeneous model. And of course, we're still going to go on and discuss the inhomogeneous model as well. But essentially, there's a state space S that is sort of partitioned into two parts. S plus is a set of discovered paths, and there is S minus, which is a set of undiscovered paths that are reachable by mutating existing seeds that we currently have not reached yet. And so together, if you were to take the union of both of these respective sets, you would end up getting the state space S. Right. And now let's look into the stationary distribution, right? And so with fixed probability, right, with fixed transition probabilities, the stationary distribution exists. And so we're able to tell if a path has been overvisited or has not been visited enough, right? And so as we contribute more energy to fuzzing seeds, we end up realizing, okay, there are certain paths being seen more than other paths. And so this allows us to get the information needed in order to make the decisions within AFLFast when to redirect the actual energy. Now let's talk about the time inhomogeneous model. Essentially, as we continue to fuzz a seed, its corresponding mutations will end up replacing it. And as a result, as we keep replacing the seed with each mutation, the actual transition probabilities may end up changing. And if these transition probabilities change, it is more realistic and it corresponds more to the fuzzer behavior, but it introduces a lot more nuance and rigor to the model that make it harder to analyze. And actually, we're going to look into an example to describe this. Let's say the program we're trying to crash here, crash me, right? And here we see that, the input in order to crash is bad, exclamation mark, and let any other character be an asterisk. And so we start off with some jargon, um, like some random four-letter word that doesn't have any of the corresponding letters, right? And so the probability to end back in that situation is sort of given here, 1 minus 2 to the power minus 10. And this indeed is a homogeneous model, right? And so the inputs at each state are the same. So going from here to here allows the probabilities to remain the same. However, let's say in this case, I mutate, let's say here I have Bill, Bill. So 3 of those letters would be an asterisk. And then I were to do BZLL instead, that is a new mutation, and that were to replace this node, what would end up occurring? Well, that depends on the mutation strategy. And we know that Z, for example, is more towards the end when it comes with the MASCII value chart. And so if we're mutating based on that, then it might take longer to actually get to the corresponding, input necessary to move on to the next state. And so that might add more of a barrier and change the probability as a result. And so here, see these values, they're constant because this is representing a homogeneous Markov chain. However, if it was inhomogeneous, that introduces another layer of complexity. And of course, there's a challenge with coverage-based fuzzers, right? And so essentially, coverage-based Greybox fuzzers are just an ensemble of random walkers in a Markov chain. We're constantly exploring paths. And so now let's go for the challenges of coverage-based fuzzers. So a coverage-based Greybox fuzzer, within the paper is sort of denoted as a ensemble of random walkers in a Markov chain. And the goal here is to find some interesting path S in S minus that has not been discovered by any other seed, you know, lowercase d within, the set uppercase D of test cases. And AFL, as we sort of discussed originally, has a very constant way of assigning energy to seeds and exploring them, right? However, in order to reach some, path, I to j, there is a minimum energy. And if that minimum energy is not, supplied, then we might not ever end up discovering it. And that leads to um, higher density paths being constantly explored. And so we could end up in a situation where AFL is assigning more energy to paths that already have been overexplored, and less energy to the paths that really needed to begin finding new vulnerabilities. And so here's the first example of too much energy assigned. Is this is referring back to the Crash Me program of bad exclamation mark. We start off with one test, right? Just some random string. We mutate it, and then we continue to fuzz it. And note that the AFL fuzzer assigns around 2 to the 16 as the energy for a test case. So that's how many mutations are generated from it. And using the transition probabilities, we're able to see, okay, so we're running to the 16 plus one tests. Um, we end up at this state, and these states are the ones we end up exploring. And then we keep on doing that subsequently, and eventually we'll end up reaching that exclamation mark. But as you see, you see that the total number of test cases explored is 4 times 2 to the 16 plus 1. If you do the math of the expected minimum energy to achieve, this crash, or to achieve finding this path, it should only be 4 times 2 to the 10. And so here you can see there's a substantial overspending of energy in paths that are not needed, or it's not necessary for. And then there can also be a situation where you're assigning too little. In this case, this is key where you're assigning 512, so 2 to the 7. I mean 2 to the 9. And essentially, we start with BA, right? And using transition probabilities, we end up creating um, a lot of seeds like, the 4 asterisk, just a bunch of nonsense, and then B triple asterisk, and then BA double asterisk, and then barely any, well, nothing, bad asterisk and bad exclamation mark. And however, we do discover 2 more mutations from this, which in row 2 and 3 we explore further. And then within those, uh, we move on to the next row and then begin exploring those as well. And as you can see, it's taking a lot more iterations to eventually reach and find bad exclamation mark. And however, this is actually not a bad thing because it lets you quickly look around in the neighborhood of a seed and quickly gauge, the properties of it, which is inherently not a bad thing. However, after a long period of time, it can actually dampen the performance. And so that is one of the shortcomings of using too little energy with the long run. Even though short term, it does provide the benefit of allowing exposure to a vast variety of seeds. And so now we're in a situation where we need to find a way to boost Greybox fuzzying based on this model, right? So let's find a way to continue to explore low density regions without assigning too much energy to these, overexplored regions. And so, this is done through improving the search strategy, adjusting the power schedule, and spending a little bit of energy to explore the neighborhood and figuring out if a path is in a high, low density region, right? Um, so from this Markov chain model, let's see how we can boost Greybox fuzzy. And so The goal here is to figure out how we can spend a lot more energy on these low density regions, these low density paths, without giving too much energy away to these more uh, higher density paths that already get explored quite frequently by vast majority of inputs. And so essentially it's finding how to redirect this energy. And in addition to adjusting the power schedule, how can we improve the search strategy, right? And so first we need to figure out, okay, are we in a high or low density region, right? And if we are, that's going to change how we distribute energy to this region, or if we even distribute energy to it at all, right? And if it is a low density region, spend even more energy. And there's various protocols to approach this, right? And so this is governed via a power schedule. And there are various algorithms for power scheduling defined and referenced within the paper, right? There's a exploration-based constant scheduler, cutoff exponential, linear, and quadratic. And we'll briefly go over these, talking about the notation and syntax that sort of comprise these various scheduling algorithms, since it can be a bit vague and hard to interpret within the actual paper. And so a explore-based constant scheduler is basically what the original fuzzer is doing. We're just increasing by some constant, right? Um, However, we might reduce how much we're distributing to each seed, so using less energy than spending a lot more. Right? And so we're trying to reduce overspending on certain inputs and explore various inputs much faster. And so this sort of ties into the chart of how we were exploring a lot more inputs and seeds when we were spending less energy per seed. Right? And this is, of course, beneficial, trying to go through and explore various seeds and not trying to spend too much time overspending on certain ones. And then we have cutoff exponential. Here, beta is greater than 1. And then we calculate the mean as sort of the, the frequency on average uh, of all paths I within S plus. That was the average on how often they show up. And if we realize that the current path for this input is above the mean, then this sort of dictates, okay, we are in a high density region and we should not spend any energy. And so this is a much more aggressive approach, a all-in approach on exploring rare paths, right? So in this case, you would default to using the minimum of either EC alpha of I over beta, which is the previous power scheduler, where I forgot to define here, alpha of I is the original energy distribution used within the AFL fuzzer. So essentially dividing it by some value beta, you're reducing the amount of energy per seed. It's still constant, just a smaller value, times 2 to the power of the amount of times this seed has been picked. And essentially you end up finding a lot more energy to these smaller cases. Or if M is smaller, you would do that where M here is your cutoff, right? So you wouldn't do it past a certain point, so you wouldn't go too extreme, right? And as you can see here, it does yield interesting results. If you look in the left-hand corner, you end up following that minimum expected value that we saw before, interestingly enough. And the exponential scheduler takes essentially what previous one was doing. However, we're we're not going to completely cut off inputs from getting any energy. Instead, we'll take into account how much energy it has received at that point and use that with my calculations to reduce. So naturally, lower uh, dense paths will receive more energy than higher dense paths, just because of the fact we're taking f of I in the denominator to reduce energy to these high density paths. And so we're sort of maintaining this inverse relationship. Higher density paths lower energy, lower density paths, higher energy. And there are two other forms of schedulers here, linear and quadratic, right? The main ones discussed and used in the paper with respect to AFLFast is exponential, and the results um, that AFLFast discusses are regarding the exponential power scheduler. But here we have linear and quadratic, where it's essentially the same, except you're not doing as sharp of a change. And they also map these against the performance of AFLFast, which is, of course, using an exponential power scheduler, and see quite an interesting trend in the differences between these various schedulers. Right. Of course, there are some, you know, flaws in the paper itself. The Markov chain model itself is very loosely based um, in reality in itself, and so it doesn't exactly represent how the fuzzer naturally behaves, right? And so, of course, there's several compromises made of sort of going back from this inhomogeneous model that actually represents what the fuzzer behaves and moving back to a homogeneous model. And of course, this is done through various assumptions. You're assuming some level of symmetry, and you're assuming the way bugs are sort of distributed amongst these paths. And within the paper, actually, if you look at the evaluations later down, where they talk about their testing process and so on, they're only testing it on a very small set of software, and so there's not much done to sort of broaden the scope of what's being tested on, right? Which I mean, in the given context, I guess there might be some justification for that, but the evaluation isn't as broad. It doesn't test various. Uh, it's not really diverse in what it's testing. And the paper itself does not have any sort of critiques towards itself or any sort of discussion regarding that. It does discuss its results. It does discuss, sort of the reasoning and builds up from, you know, the original AFL fuzzer and mapping that over to a Markov chain model, and then from that deriving what it needs to in order to create something better, and so on and so forth. But it doesn't discuss the inherent downsides, which in itself does raise some flags. However, the main purpose of the paper was to provide some sort of theoretical backing and foundation, which it did do and has served as essential citations for other papers down the line. And so here's some citations of course, the actual paper and then the image of the one graph I used within the Markov chain slide. The, the other various images were, of course, from the study itself, hoping to reduce the technical overhead needed to understand the study. That was the main point, and hopefully you can go in and dive into the actual study and understand the details much more thoroughly, because there is quite a bit to it. Thank you for watching, and I hope I was able to provide some sort of benefit.